So we're going to take another derivative of one of our vector value functions, and we're going to apply the cross product this time. So this time we're trying to find the derivative of u of t cross u prime of t. And what we're going to do first is we're going to look back up and we're going to utilize this formula that if we have r of t cross u of t, r cross the derivative plus r derivative cross u. All right, so essentially in this time we're going to replace u, or r with u, and u with u prime. So essentially it's like the product rule, except we're using cross products. All right, so a generic formula that we can try to spit out from this would be equal to, we would say u cross u double prime, so it would be u of t cross u double prime of t plus u prime cross u prime. Alright, so that's the formula we're going to use, which means that we have to find u, u prime, and u double prime to be able to substitute into this part of the formula. So we go back up, and first we remember that u is t squared minus 2tj plus k. So that's, remember that u is t squared I minus 2tj plus k. All right, and just to remind me, that is u t squared minus 2t plus k. All right. U prime is going to be equal to 2ti minus 2j. And then finally, u double prime is just going to be 2i. And we're just going to throw all of those back into our determinants. So we're going to first find u cross u double prime. And since we've done this a number of times, this shouldn't be too difficult. So we're just going to take our coefficients of ijk. So t squared minus 2t and 1. And then 2, 0, 0. And if we go through and compute, then the I component's easy. When we cross those, that's just going to be 0i minus, if we cross the components to get j, then we're going to end up with a 0 and then a negative 2, so it's going to be minus a minus 2, which is going to turn into positive 2j. And then finally for k, we're going to cross, that's going to be a 0 minus a minus 4t, so that's going to turn into plus 4tk. All right. Now we also need u prime cross u prime, right? And we're going to find something special happens with this one, although if we go back to section 3 where we talked about the cross product, this shouldn't be a surprise. So it's going to be minus, or just 2t minus 2. So we have our 2t, and then we have a minus 2, and then we have 0, and then 2t minus 2, and then 0. And when we find the cross product of this, should be pretty easy to see that it's going to work out that things are just going to cancel out. So this just becomes a 0i. For j, that's easy enough. That becomes 0j as well. And then for k, we're going to get minus 4t minus a minus 4t. So that's 0k, which is equal to the 0 vector. One of the rules you might remember is that, and we might have proved this one, is that when you cross a vector with itself, you always end up with the 0 vector anyway. All right, so thus that means that if we find d of u cross u prime, which was the original problem that we had, right, so remember we're finding u of t cross u prime of t, then that's going to be equal to, remember we had 2j plus 4tk, so that's 2j plus 4 tk plus the 0 vector, and we just end up with this. Okay, so that's not too bad. All right, so moving on from some of the derivative rules, now let's start talking about the idea of integration of vector value functions. And much like differentiation, integration is going to be term by term. So essentially we're going to integrate I terms, we're going to integrate j terms, and we're going to integrate k terms. And that's how we're going to find the integral of a vector value function. If it's an indefinite integral, at the end we're going to put a plus c, because there is going to be some constant to which we're not sure of, and they're all going to be c1, c2, c3s. We're just not necessarily sure what those constants are. If it is a definite integral, then each of these is going to have their own constant. So there's going to be a c1, a c2, and a c3 for these definite, or I'm sorry, there's not going to be any of those. That's for a different type of problem. Excuse me. So just ignore that. That's the initial value problem, so that doesn't exist. Sorry about that. All right. So let's just take a look at a couple basic examples of being able to find our antiderivatives. All right, this first one's going to be really easy. So we have sec squared t plus 1 over 1 plus t squared j minus k. And we could just integrate term by term. All right, so that's really the same thing as the integral of sec square ti dt plus integral of 1 over 1 plus t square j dt, and then we'll just pull the minus out front, minus integral of 1k dt. And all of these are really elementary antiderivatives. So you might remember, antiderivative of secant square is going to be tangent of t. Antiderivative of 1 over 1 plus t square is going to be the arctangent of t, and that's j. And then finally, the antiderivative of 1 with respect to t is going to be a negative t, right? And then we just have this constant of integration, right? So that's all we have to do for that one. Just a really simplistic example of how to go through and do by term integration. All right, now, a little bit tougher example. We have this definite integral, 0 to pi fourths sec t tan t I plus tan t j plus 2 sine cos k. All right, so we can break this up into 3 separate integrals and then evaluate. So let's just do that. So we have integral from 0 to pi fourths of sec t tan t dt I. And we know the antiderivative of secant tangent is just going to be secant, since the derivative of secant is secant tangent. So that's sec ti from 0 to pi fourths. And then let's just go ahead and immediately substitute that in. So it's going to be equal to sec of pi fourths minus sec of 0 I. And this is where we might want to have our unit circle. Now remember, secant is the reciprocal of cosine. All right, so really, if we know what 1 over cos of pi fourths is, well, that's going to be 1 over root 2 over 2, which is going to be 2 over root 2. All right, so one way to write this would be 2 over root 2. And we know that the cosine of 0 is 1. So we would basically get the reciprocal of 1, which is 1. All right, so we can leave it like that. If you were to rationalize this, you end up with the 2 roots of 2 over 2. So another way to write this would be root 2 minus 1i if you were to rationalize it. Okay, so that's the first part. Okay. The second integral, 0 to pi fourths of tan t. So this is where you might want to look at your basic list of integrals and derivatives, and you might see that this ends up being the natural log of the absolute value of secant of t. And it's going to go from 0 to pi fourths. we're going to use our fundamental theorem of calculus. So that's ln of secant of pi fourths minus ln of secant of 0. And the good news is we've already seen what both of these simplify into, so that's not too difficult. Ln of secant is ln of 2 over root 2. And then ln of secant of 0, we know that secant of 0 is 1. Right? Since it is 1 over cosine of 0, cos of 0 is 1, so 1 over 1 is going to be 1. Right? Ln of 1 is 0. And finally, what we can do is we can rewrite this. If we were to rationalize that expression, we could just write this as ln of root 2 if we chose to. Now remember, this is all j. All right, so I probably should have put a j somewhere in here all the way back. So I'm going to do that. All right, not that it's all that important because we certainly would remember it in the final answer. But all right, so that's our j coefficient. And then finally k, we have 0 to pi halves, or pi fourths, excuse me, of, we have 2 sine t cos t, I believe. Yep. Now, to be able to evaluate this one, it's not basic, so we would probably need to utilize a u substitution. So I'm going to start by letting u be equal to sine of t, because I know the derivative of sine is cosine. And because we're taking it with respect to t, it'll actually be cos t dt. So du is cos t dt. And so we end up with integral, not from 0 to pi fourths, but from a to b to u du. Right? So sine t became u, cos t dt became du. We integrate this, so this becomes 2u squared over 2 by adding 1 divided by the new exponent, a to b, or just sine square of t. All right? And of course there's a k in this, all right, so similar to the previous. We're going to have our k in here, so I'm just kind of squeezing it in here. And that's from 0 to pi fourths. And so eventually we're going to end up with this sine square of pi fourths minus sine square of 0, k. And don't forget that a way to think of sine square to the pi, or sine square of pi fourths, is sine of pi fourths square. So just algebraically, just to help you out with this, this is sine of pi fourths square minus sine of 0 square, k. If that helps you to think of how to evaluate a trig function, squared or cubed or anything like that. Now we know sine of pi fourths is root 2 over 2, so this is root 2 over 2 squared. We know that sine of 0 is 0 squared. And ultimately, that just works out to be 2 over 4, or 1/2 k. And so finally, we can put this all together. And our answer is going to be, we're going to go all the way back up. And remember, we had root 2 minus 1i. And then we had our ln of root 2j. And then finally for k, we had our 1/2 k. So hopefully that gives you a good introduction to being able to complete antiderivatives with respect to these vector value functions. The next step is to be able to take these and make them into initial value problems. So that'll be our last 2 problems in this section.